Thank you for inviting me to talk. And I was saying at lunch that I found out this morning that actually working on cancer is working on the symptom and not the cause. So since the cause is actually aging and cancer is just a byproduct. But anyway, so I was going to talk about cancer stem cells, and we'll see whether Dr. Levine has fundamental disagreement with what I'm going to say or not. Probably so. Let's see. So just you're moving it by the arrow, or you're moving it here? So as was mentioned earlier this morning, I mean, the whole concept of stem cells has been very well worked out in the hematopoietic system, in which you have these early stem cells that are self-renewing and then give rise to later multipotent progenitors that are the ones that really divide and then differentiate into the cell types that we all know and love in our bone marrow and circulating in our bloodstream. So that system is well worked out. And then a few years back, 10 years ago, the idea resurfaced after a period of some years that maybe this sort of model fit for cancer. And so it became incredibly popular and got very well funded, and it was actually annoyingly popular for some of us who had been working in cancer biology a long time. So the fundamental properties that are described for stem cells is that they have long-term self-renewal. They have to always be there, as we've talked about already this morning. And they have to be pluripotent. They have to be able to give rise to the rest of the tissue. They have to have asymmetric cell division in that they have to give rise to themselves again. They have to be relatively quiescent, although your model with the p53 maybe inducing part of the stem cells to differentiate was a different model than what this is. This is where you basically give rise to one cell that's going to become a progenitor, and the other cell stays very stem-like. And then resistance to drugs, perhaps by ABC transporters, active DNA repair capacity, and resistance to apoptosis. This was sort of the official list of all the characteristics that a cancer stem cell must abide by. Now, the idea of asymmetric cell division seemed to me fundamental to this whole cancer stem cell concept, in that you would have to be able to replicate itself or you would no longer have a stem cell there. So some work has gone on saying, how could we have actual asymmetric cell division? And it's basically based on polarity, and it could be either due to the microenvironment. I don't know if this little pointer's working, yeah. Either due to the microenvironment or something inside the cell that gives rise to this polarity that allows not all the same transcription factors to end up in the daughter cells, and not all the same epigenetic marks. So one or the other, either extrinsic or intrinsically, you end up with two different cells after that cell division. Well, this was our traditional model, and I got frustrated when the whole cancer stem cell concept was first brought out, because it was essentially setting up a straw man, and people said, well, the old model is that every cancer cell divides and forms two new cells. This was essentially the old model. And having worked at trying to clone cells for a long time, where you put one cell per every 3 wells in a 96-well plate, and all you end up with is basically one clone, or even in a big dish where you put very few numbers of cells and all you end up with 1 or 2 clones. I said, nobody ever thought that every single cell gives rise to other cells. So it was essentially a straw man that was set up. And if you're British, it's called an Aunt Sally, but, which I didn't know. But in any event, that model is not what true cancer biologists ever thought was really going on. People thought more of a stochastic model, which is that all of these cells can divide, but they may not all give rise to subsequent cancer cells. They may not all keep growing. So in any event, this is again back to the two really very different models. So the stochastic model is that sometimes you'll have a cell division and the other cell just won't make it, can't keep going. It'll be random which cells in that process go on and make an actual tumor. Whereas the cancer stem cell model is that only the cancer stem cell, not only does it have to replicate itself, it's the only one that can go ahead and make a model. Now you might say we're physicists and we should be able to, or biologists, whichever, be able to prove or disprove this, but I think it's been incredibly hard to prove or disprove these models. But for us oncologists that treat cancer, it's really important to know which one is correct, because the idea that here's your cancer and you have a few little cancer stem cells sitting in there that then can survive your treatment and then replace the tumor, that means that we need to try to target these cancer stem cells for treatment and that we don't have to worry so much about these other tumor cells. That would be the reason why we need to know if this model is true or not. Then we need to know whether we're spending time working on these little stem cells or we're spending time working on the rest of the tumor cells. And I just wanted to point out, while people have been going at the stem cell thing for 15 years now, this was actually most recently on a website of Robert Weinberg, so really still completely unresolved. Do we have these little stem cells or don't we? So here was the typical assay that's done for looking for these stem cells. You look at different phenotypes and sort them, subpopulate them into cells that will or won't make tumors in nude mice. So here is yes tumor, here's no tumor. And the cells, non-tumorigenic, happen to be CD24 negative, in this case CD24 positive. And these are breast cancer cells. And so this was considered very solid evidence at the beginning when this was published, 2003, that the CD24 low actually would cause tumors very frequently, and the CD24 positive cells would very rarely cause cancers. And then people started looking in every tumor and found really evidence of cancer stem cells everywhere else, in bone marrow, in breast and brain and colon. And they also substituted another assay called the floating sphere assay. If a cancer cell in a dish can form a sphere, then that's also evidence for cancer stem cell. And here's pancreatic cancer doing the same thing. In this case, it's CD24 positive. So, but some problems have been coming up over the last 15 years as we've been talking about this model. One is that a number of cancer stem cell markers have been described and then found not to be specific. Or as I just showed you, CD24 positive in one cell type, negative in another. The tumorigenicity assay I'm going to show you has been found to be very dependent on experimental conditions. Epigenetic regulators have been found that can switch on or switch off the stem cell properties, as we heard this morning. And then emerging molecular data support a clonal evolution model. And finally, some of our data showing that growth rates favor an exponential model. So cancer stem cell markers, you can see here a recent publication showing all the different markers that have been reported in different tumor types. Some of them are the same, and some of them are different. It's just a broad array. There's not, and so I think it's interesting that the LGL marker that you were mentioning this morning is not in here. But there it is, LGR5, so it's in one of them. But one of the ones that we got interested in was the ABCG2, which is an efflux pump, which is a multi-drug efflux pump that was responsible for making the side population in a flow cytometry assay. So this was found to be present in a number of tumor types and in a number of cell lines. So this was the second thing that really bothered me about the stem cell concept after the whole stochastic model point, and that is that I knew from being a drug resistance person that these things are found, this side population, this so-called 0.5%, depends on what cell line you're looking at, and you can find very high percentages of them. Depends on what their level of expression is. So in this case, we're looking at some cells that are more drug resistant here than a less drug resistant line. But this is a histogram. We're talking about the lowest fraction of a histogram here, and here a greater percentage of the histogram. So how is that a stem cell population? And then more recently, data from TCGA, which is looking at literally, this is about 2,000 patient samples. And here you can see yellow is kidney cancer, and pink is breast cancer, and purple is pancreatic cancer. So ABCG2, which is the pump that we were just looking at, is in very high expression, a 1,000-fold range of expression across tumor types. So here we have a putative stem cell marker that also doubles as a drug resistance gene that's expressed again across all cancers. And here's glioblastoma, which in itself has a 64-fold range. This is most glioblastomas here are in the circles, and the squares are the low-grade gliomas. Very high expression of this multi-drug transporter. So, and then we also, years ago, did a SAGE analysis, which was a gene expression type of analysis, and comparing that to just in general drug-resistant solid tumors. And what we found was that stem cell marker I showed you a few minutes ago, just like ABCG2, also in the whole population, and correlating with 5-year survival. So it doesn't quite make sense that you would, on the one hand, have this small set of cancer cells that are stem cells with these markers, and on the other hand, these are poor prognostic markers for the bulk tumor population. And then another fly in the ointment to me is the tumorigenicity assay. So here was an initial report saying in melanoma B5, ABC-B5 positive cells were the tumor initiating cells. And you can see that basically you had in 10 to the 6 cells, you could get tumors if you were in the B5 positive population. So the idea was that 1 out of 1,000,000 cells were actually tumorigenic stem cells, so very low rate. Then they switched mice, and not just NOD-SCID, but also IL-2 receptor gamma mice, which is apparently another level of immunodepletion, decreasing the immune system. And all of a sudden, the stem cell frequency was 1 in 4. So how's that the stem cell when that's actually more relevant to what the host is? Then this business of 1 or 2 or 4 genes being able to induce pluripotency makes me think, okay, how do we have a defined stem cell population when we can create it from simply turning on 1 or 2 genes? And that's what cancer does best, is turning on 1 or 2 genes. And this is a paper that hasn't been submitted yet, but from a friend of mine who basically created stem cells from glioma cells just by starving them, which is sort of the opposite of the P53 from starvation. So I didn't quite understand why this model is different. But nonetheless, the point being you can create stem cells out of your culture conditions. And then finally, the clonal evolution model, which is, this was one of multiple papers that have come out with different leukemias. And what they've done here is looked actually at fish, at very detailed, each one of these is a single leukemic cell. And then they counted them all and then, classified them. And what they found was that in every diagnostic sample of a leukemia, all of their leukemias, they would have multiple subclones. There would be the largest population of the leukemia, but many other subclones with it. And then often after treatment, they would then see only one of the subclones that was there before reappearing, and then with it other new subclones, suggesting that basically the leukemia went through a bottleneck like this. So you have multiple subclones, here purple, here gray, and the gray are the founder clones. And these are distinctive genetic differences. And then only the yellow actually makes it through this bottleneck, which is the treatment and the relapse. So it's a multi-step nature of cancer. So what I was going to show you now is some data we've derived working with Creston and working with some other people in our group, looking at models of cell growth, of tumor growth, actual patient data. So Wilfred Stein originally came up with this model, and what we gave him was tumor measurements for patients over time. And this is that's the summation of this curve. He basically said, what you've got when you treat a patient is that their tumor goes away, Then it comes back. Those are two curves. He said, I can mathematically break that down for you. Now, I'm not a mathematician, but I believe him. So this can be broken down into growth and regression. And then this is the equation, and he says this proves that the growth of this patient's tumor is exponential. And the decrease is also exponential. So then we spent a lot of time fitting data to these models. And here's another model with Creston that Creston also agrees that growth is exponential. So it's nice to have another whole separate view of that, seeing the very same thing. But we derived some sub-equations from those first equations, and you'll understand this better than I do. But where you have growth without decrease, decay being tumor regression, so you can have growth without the decay, you can have decay without the growth, and then you can have a long period of time where you're waiting while the tumor is suppressed. So, and then there is also the linear equation, which if it were linear and not, if it were asymmetric cell division, you would have linear phase. So this is how we fit these curves, and you can see this curve being, this is an individual patient being a decrease and a regrowth, treatment and regrowth, and this one never regrew. Depends on what disease you're treating, whether you see the regrowth or not. So this is a paper with Creston. So Creston, if I don't explain this well, you can correct me later. So a lot of work has gone on that we've put into analyzing different data sets of patients, different diseases, different cancers, and we see over and over again that the growth rate, not the regression rate, but the growth rate is what correlates with survival. The faster the cancer grows, the more likely the patient is to die sooner. So we then now have looked at over 3,000 patients and divided the patients into each of these different equation models that I just showed you. And what we found is that only 8% of patients actually fit with this linear equation, which is more than we originally thought we would actually find. And all the other patients fit the other models. And of course, if we get more lymphoma samples, we're going to get more examples of patients that respond, have regression, and never regrow. So this is more a reflection of the types of data sets that we have. So the distribution is not what to think about right now, but just that all these different types of patterns can be described in patient data sets. So here are the data sets that we have. And the ones that actually have that linear growth, which could be the stem cell self-replicating, are the D0 prostate cancers. Those are prostate cancers that are not detectable. They've been treated, and they're not detectable except by a change in the PSA. There's no visible tumor in the patient. So only 82 patients here in this data set, and 79 patients in this data set. The D0 patients were the ones that fit the linear phase. So together, I think that what we, I don't remember what's that, yeah. So together, what I would say is that the vast majority of patients that we treat in oncology clinic, their data fit an exponential equation. And the growth rate constant derived from that exponential equation correlates very well with survival over and over again in data set after data set. So we think that this means that patients die from the exponential compartment. So if that original model, Weinberg model I showed you is right, we still have to pay attention, or we need to pay attention to the exponential compartment, because that's what patients are actually dying from. And if there's a stem cell compartment, it's not affecting the tumor kinetic profile at the time we see the patient in oncology clinic. Now, it may be that that is the time when the cancer is truly eradicated. There may be a stem cell compartment at that point in time, but it doesn't argue that we can turn to only studying stem cells. And just to acknowledge, though, that by having looked at the stem cells and the field having spent time on this, have derived a number of pathways that are called Stemness Pathways. And basically those include the Wnt pathway, we talked about this morning, and the patch and notch pathway, smoothen pathway. So those were not really understood as cancer, important part of cancer biology a decade ago. So that's been the real value of studying the stemness pathways. But exactly the contribution that inhibiting these is going to make, we don't yet know. It depends on whether we decide that perhaps a prevention strategy would lie here. So far, the disease that in the hedgehog mutations, basal cell cancer, there is actually a drug that inhibits hedgehog, and so that has been successful in the clinic. But that is the only thing so far that's been translated clinically. So those would be my conclusions. As I've mentioned, I think it's hard to apply that strict stem cell definition, and patients die, I think, from the exponential phase of tumor growth. We have some new pathways, but we still have to figure out what the role for those is going to be in the clinic. And I just acknowledge all the people that have worked with us on this. And I left off Julia Wilkerson, who's done a lot of the mathematics of this. So that's it.
Questions?
It's hard to see.
Yeah, if I remember correctly, the literature on cancer stem cell literature is vast. Mm-hmm. It was a movement, or still is. Mm-hmm. Now, I'm a little...
And I've just captured the high points for you.
No, I understand. I'm having a little trouble grasping what the difference is between whether you're a believer or a disbeliever in your function as a health person.
You mean what difference it matters?
Yeah, what difference it matters.
I think it, other than being insulted by the original model, I think the difference depends on what kind of drugs you want to take to the clinic and what you want to study in your laboratory. So do I want to study drugs that will, tackle this? What I'm saying now is I think our data suggests that this exponentially growing population is the population that kills people. So those are the drugs I want to study. But other people say, well, these are the ones that survive, like the D0 prostate, which is when you have no detectable prostate cancer, but just a blood marker. Those are the ones that they want to study. So, it just requires a lot of work to get to the point where we know the real truth. Will we be able to target these cells and do anything about cancer when a patient comes to us who's got 5 different tumor masses in their lung and 4 in the liver? Those patients I don't think are going to be helped by this. So it just depends on what you want to work on.
Okay, so it has to do with drug design therapy then? Or drug design
you
strategy?
Mean sorting out the truth of this model
Yes.
has to do with what we put our resources behind.
Gotcha, okay, thank you.
Any other questions?